So in this video, we're going to look at various different types of controllers. Now, as we go through this, we want to keep in mind that there's lots of different controllers. And so the idea is that we'll want to choose the right tool for the right job or the right controller for the right application. So just this slide here, right, we're looking, we see obviously there's a flat tire, and I have two different tools. I have a tire wrench, a lug nut wrench, and a pair of pliers. And so if you can imagine which one of these would be the best tool to take that tire off. You know, obviously the tire wrench was designed specifically for removing lug nuts, where the little pliers there would be almost impossible to try to get lug nuts off of. But on the other hand, there's some tasks where getting, uh, you know, using those pliers would be very useful, and the lug nut wrench would be completely useless to on certain tasks. So, you know, kind of keep that philosophy in mind as we discuss the different types of controllers and things as we go on here. So, well, you know, normally as before, we'll look at a little bit of terminology and then look at a lot of different types of controllers here. So to start off, for a definition for a controller, it's a device designed to perform control of a system, obviously. And for this class, we're looking specifically at electronic or digital, meaning like a computer device that reads inputs, has some sort of program inside of it that reads and those inputs, considers what they are, and then decides what action to take and is able to send those actions out to have something done. All right. Now, when you're talking about creating a program, okay, so a program is what we normally kind of call it when we're creating our control system or set of instructions. So a program is like a set of instructions that we want to be performed. And so we can do this using what we call dedicated code. Okay, so certain types of controllers, you just write the program and it does whatever you want it to do, and that's it. And the controller will do nothing else but just run this one program. Now, it could be a fairly large, complicated program, but it just runs this, does nothing else. The other paradigm is to use a computer with a operating system. Right, so if you think about like the Windows operating system or the Linux operating system or your Mac operating system, right? So there you've got this base operating system, and it can have a lot of advantages because it has lots of built-in like networking, troubleshooting type tools. You know, you got the ability on that to just pop open a browser and search for something if you have a question. You know, and you have network, internet access, things like that. But the downside of the operating system is the fact that usually it's a multitasking program, and so you create your program and you run it on top of this operating system, but this operating system might be doing things that is delaying your program or preventing your program from accessing certain parts of the computer system. So, you know, again, there's pluses and minuses for each of these. Another thing to keep in mind is the execution of timing. Okay, so for instance here, we can do what's called sequential programming, which means that we just run down through a list of actual individual programs or individual tasks. Sorry, we run through a set of individual tasks. And so you kind of start at the top and just sequentially go down, and then when you get to the bottom, then you're going to go back up and go through them again. And part of that is like looking at inputs, and so like here, I think I showed you this on the first lecture, right? We have this tank, and this tank is like overflowing with antifreeze, which obviously is not an ideal thing to happen, where you got hundreds of gallons of antifreeze just flowing onto the ground. So if you think about, I have a controller. So if you look at this box here, let's just say in this box is a controller, and at the top of the tank I have a sensor, and this sensor is supposed to send the message down to the controller and say, hey, the tank is full, shut off the pump and quit putting more antifreeze in it because there's no room for it, right? So when you run down through the program, okay, it checks the sensor and says, okay, well, the pump is full, or the tank is full, shut off the pump, right? So the message the tank is full comes into your controller, comes down into your controller, then your controller says, oh, well, let's shut off the pump. And, but, you know, like a minute before, the tank wasn't full, and so it did not shut it off, right? So, but then it comes back up and loops around and checks again. On the other hand, we could use what's called an event interrupt driven system, where the sensor, when the sensor notices that the tank is full, it sends an interrupt to the controller and says, hey, you know, the tank is full, shut off the pump. And so it kicks off this other task. And so in some ways, maybe that sounds like that might be a better solution than just running through all these tasks, and you already checked up here and the tank wasn't full, so you didn't shut off the pump, but now you're doing all these other tasks, and then you got to get to the bottom and go back up and check. Okay, but you can look at it the other way too. It's like, all right, so we run through our tasks, and it only takes, say, 30 seconds to run through our tasks, or, you know, usually actually it's going to be in milliseconds or something, not seconds. But we get to the bottom when we go back up, and then we say, oh yeah, the tank is full, we can shut it off. Where on the event interrupt, maybe you have it come in, your sensor generates this event and says, okay, the tank is full, shut off the pump. But before it actually gets to the point to go shut off the pump, we get another interrupt from something else that says, hey, take care of this. And so now you're interrupting the event to shut off the pump, which was very critical, and possibly that other event was not so critical. It could have waited. So, like I say, there's just two different things to keep in mind. So remember that we talked, I believe, on the first day a little bit about this tank and about the real-time control. And the idea here is the fact that a lot of times now we use this real-time you see it on the internet and stuff all the time. You know, it's like, oh, you can watch the football game or the Olympics or something in real time, and you're watching these athletes, you know, perform and stuff in real time. But in reality, that's not always real time, and there's a delay, right? For the, you know, if we're watching the Olympics in Paris or wherever they're at, and then the you know, just for the video to be sent, you know, across the Atlantic Ocean to our telephones or our TVs where we want to watch this at, there's a delay. So there's just an inherent delay in getting the information. But a lot of times there's also a intentional delay where the broadcasters, the TV stations, or whoever are broadcasting this actually build in a delay. So usually instead of watching it live, you're watching it maybe, you know, 2 minutes or 5 minutes behind when it actually occurred. And some of that, you know, there's lots of reasons they do that. It gives them kind of time. If something goes wrong, they can maybe hopefully correct it, and then you don't notice the lost data hardly at all, or things like that. But for whatever reason, there's sometimes inherent delays in that. All right. So, but for us, when we talk about real time, we want to talk about what I'd like to call hard real-time control, which means that you are guaranteed that the event will be addressed within, say, 30 milliseconds or something. The exact time depends on, how much time it takes for, like, say, where in this case with your sensor, if you got your sensor at the top of the tank, you know, you don't have it at the very, very top. You have it maybe an inch or two down. So then that gives you a little bit of time there between the sensor sending the message to the controller to shut it off before it is actually overflowing, right? So, you build into it a little bit of delay time that's okay. But then you run this controller that you know is going to get back up to the top of that event if it's sequential, or have time to take care of any other interrupts and get back and finish shutting that pump off before the tank actually overflows. All right, so we're going to look at a bunch of different classes of controllers here. I have them listed here, but we're going to look at each one of these in on a different slide. So I'll just move on. So this is what we call a PIC microcontroller. So the idea of these microcontrollers is you've got everything is all on a single chip. And so it's like you have like an oscillator, which is your clock that drives your computer, your processor. So remember, we talked a little bit about that back in the binary lab. We talked about flip-flops and how these flip-flops are memory devices, little electronic memory values that are driven by a clock. So that's what this oscillator is your clock signal to control those. But then we have our CPU, but along with our CPU we have RAM. So here we have the RAM holding our program and any data that we need that's not actually coming in. And then we have lots of different I/O ports. Okay, so these ports here, this is we'll get into these in networking a little bit and stuff, but like SPI and I2C are kind of like little communication buses. USART, that's a serial bus communication. So we just have lots of I/O. So we have everything built into this one chip. Okay. The advantages of these is that these chips can do quite a bit, and they're very, very inexpensive. Okay. So this block diagram we're looking at here is for a PIC, which is a programmable integrated circuit. That's what PIC stands for. And this one here particularly is made by a company called Microchip. And they make, I don't know, dozens, even 100 or more different types of chips with different types of I/O and different amounts of I/O and a lot of different things. So the idea is you can pick whichever one maybe is going to fit your needs best. So we have lots of options, lots of I/O, very low cost chips, and they also use very little power. And they typically will also have like a low power mode where they can kind of go down into this kind of sleep mode and then be recovered from that when an event happens. Alright, so on most of these slides I'll have some links below that'll take you to more information about those. Alright, so here is a little project that I worked on for charging and discharging lithium-ion batteries. And so right in the center here you see a PIC microcontroller. This was actually a 16F876. That was the model number of it. And this was a very nice little controller, and the wiring job maybe wasn't the best here, but I used this to actually charge and discharge lithium-ion cells for a study that I was doing. And so, the idea is here's the chip. You can program this chip and then plug it in, and you can't actually even program them when they're in place, but and then this was like running some LEDs telling me the status of where it was at within the program. And then I just have some various different capacitors in here. This particular one, I did need to wire up a crystal here as part of the clock mechanism for the oscillator. Okay, so this is a crystal here. But the idea is, if you're going to make up, you know, dozens or hundreds of these, and they're all going to do the exact same thing, that's where these microcontrollers become in handy, because you program it, you get it tested and debugged and working the way you want, and then you can, you know, buy hundreds of these chips and download your specific program to them, and they're all going to work the same, very reliable, very low cost. Okay, but they're not like high processing power on here. You know, it's nothing like the Intel i7 computers or NVIDIA chips or whatever in there. These are just dedicated controllers. All right. This is just showing the I/O of the PIC microcontroller here. So you see we have these different ports. The A's and B's are the ports that you kind of saw in the block diagram 2 slides back. We have the oscillator clock connections over here. We have the serial connection here. SDI is for the SPI communications. You know, you don't necessarily need to use all of them, but you have analog inputs, analog outputs, digital inputs, digital outputs, just lots and lots of I/O. All right, the next one I want to talk about is a PD. PD is kind of a general term for a programmable device. Okay, so again, this is kind of like the microchip, where it's a dedicated sort of processor chip that you can get. There's a DSP, which stands for digital signal processor. There's PLD, which is a programmable logic device, and FPGA, which is a field programmable gate array. And so each one of these are kind of like a chip, like a processor that is going to, you know, perform a certain dedicated task. And then the idea then is that you can program it to do that task, and it does it very well. It does it extremely effectively. Okay? And so again, this type of device is, you know, typically what you're going to want to do with this is, like, if you're planning on designing hundreds or thousands of these things and, you know, selling them or something like that. So I've got a couple of examples here. This here is a Midas M32 mixer. Okay, so this is for mixing audio. And so the idea is that you can have 32 inputs. So, you know, if you have a band and you have a guitar, you have a couple of electric guitars, acoustic guitar, you got a couple keyboards, you've got drums, you know, so you got like a bass drum and a tom and a snare drum and hi-hats and crash cymbals, and each one of those, and you're going to put all these microphones on these and run these all in here and then mix the sound so that it sounds good. And so that's what this is. Now, this is a pretty amazing device. This was originally designed 20 years ago or something, okay? And it uses a DSP, or actually I think it's actually got multiple DSPs in here. All right, see, but what's so amazing about this is the fact that it can bring the data in, digitize it into 48,000 samples every second for every one of those. So they call it an M32 because you got 32 channels in, but then it actually also has some auxiliary. So there's actually 40 channels that can be coming in simultaneously. You can mix those 40 channels together to get the sound that you want. And again, you're doing this like 48,000 times per second. However, it gets even beyond that, because then it runs it into a bus. So there's basically 16 buses, and then 16 or 6 more additional buses. Okay, so there's basically about 24 or 25 separate mixes. So you can be running 40 channels in to this device and recording this sound like at 48,000 samples per second. So 48,000 times a second, you're going to mix that, the amount. So if you look at this, you see these are what we call faders or sliders here that adjust the magnitude of the volume. And in this picture, they just kind of try to make them look like smiley faces. All right. But the idea is that, if you want more drum, you push this up, and you want, less guitar, you bring this down. And so you're mixing these, but you're mixing 40 inputs. Okay. So we're mixing 40 inputs coming into something like 25 different mixes, okay, meaning that the faders are different for each one of those, into 25 different mixes simultaneously. Okay, that is a tremendous amount of computing power. And your average Windows PC cannot do this in real time. Okay, we actually I actually saw a case where somebody wanted to replace this with a Mac, and so they used this software on a Mac, and they were trying to run a broadcast live, and instead of using this here, they were using just an ordinary Mac, iMac computer, and it couldn't handle it. It crashed. Okay, because the idea is we're trying to mix this music live 26 different ways, and then send that, and send it out there and have no delay, have it live. It's like we don't want to wait for it. It needs to, come out immediately. You've got the band is on the stage playing, and you need that music, that mix to go out to the speakers, to go out to all the different places where it's at. And like I say, just in an ordinary system with like an operating system like Mac or Windows cannot process that amount of data that quickly. Okay, so that's where you want to get one of these dedicated devices like the DSP in there. So like I say, that basically this Midas board, I think I'm not sure, it has like 4 or 5 different separate DSPs built into it. Alright, so I pretty much said everything on that slide. There's a newer mixer out that is by Alan Bradley, or excuse me, not Alan Bradley, Alan and Heath, which is named Advantis. And this one here, the reason I kind of have this one here is because it uses FPGA technology, where the Midas was using the DSP technology. All right, and so this one here can handle 25 billion operations per second. Okay, and again, it's using this dedicated FPGA technology to perform this. This one can actually handle 64 inputs coming in simultaneously at 96,000 samples a second. So it's twice as fast and even more inputs coming in. And then it can mix those up 42 different ways and send it out again without any delay. Okay? And like I say, even your modern Windows, your brand new modern thing is not going to be able to do that without delay. You might say, oh, well, I did it, and you did it without delay, but then, the problem is with like these operating systems, as I mentioned before, it's like, it might be running fine for a little while, but then some other thing happens and it kicks off some separate program, and all of a sudden, your stuff, maybe it doesn't crash, but it gets delayed, and you start getting this delay or just slowing down or things like that, because that operating system is like, oh yeah, you know what, I'm going to go check for an update. You know, it's like, no, we're in the middle of a concert here. We don't have time for you to go do an update, right? So these are dedicated devices to handle and process, you know, literally billions of operations every second. And we don't have time to go check a website for an update. All right. Okay, so if you have like these dedicated processors, or they could even be more of a general processor, but what they do is they mount these on a board so that they're kind of like a standalone um, computer or controller at least. And so these here we're going to talk about the Arduino. Single board controllers can use either the dedicated code paradigm or an operating system. Okay, so our Beagle Bones that we've already used in lab is actually also a single board controller. But here we're looking at an Arduino or these ESP models, and there's a bunch of others that follow this, but these are what we call dedicated code paradigm, which means you create your program, and whatever your program's going to do, right, that's all that's in this controller. And if you wanted to add something, you would have to like add it to your original program and then re-download it. Okay, so you couldn't just like, oh, download it on the fly. Where if you had an operating system interface, you know, you might be able to add some things and run some other things simultaneously to like this main program that you had already created. But with these, it's dedicated. They're just running that one program. All right. These are really cool devices. There's a lot of different ones, different models and things. I just named three of them up here, but they have very easy wiring and testing because it's all built into this single board controller, kind of like our Beagle Bones. Very flexible, and there's lots of open source code or examples out there that you can get started and get up and running very quickly. Okay, and they also provide lots of I/O. So we have this term GPIO. I don't know if I've mentioned that before. GPIO just refers to general purpose inputs and outputs. Okay, so you have these pins or connections where we can wire up like those LEDs that we used in the first lab. We were able to like turn the LED on, so we had the blue LED. So if you were looking at Canton, Ohio in January, right, you know, it was like bitter cold, and so you got this like the blue LED lit up to show you it was cold. And then if you did like Texas or Australia or something, Sydney, Australia or something, and it comes up 75, 80 degrees, and so the red LED came on, right? So it's connected to a different output. So that's the GPIO. So here is the all three of these. So on the left we have a picture of the Arduino, and you see here on the black on the two sides, those are where you would wire up your pins. The middle one is a pin layout for what we call the 82 ESP 8266, and this is a nice little board. The difference, the original Arduino did not have built-in Wi-Fi. I think some newer ones actually do, but I haven't worked with those. But this little chip here costs maybe $3 to $5 for one of these, and it has built-in Wi-Fi. You see right there it says Wi-Fi. It's got built-in Wi-Fi and Bluetooth right into it. And then it has all these GPIO pins, so we can like connect these to temperature sensors or actuators, and it has just all kinds of different things that you can do with it. And this one over here on the right is an ESP32 that actually has built right onto the board. It's got a little LED display. It has the Wi-Fi antenna here, and it also has a connection for what we call a LoRa, um, which we'll talk about this, but this is a low power or long range uh, communication protocol, and we'll actually use one of these later on in the class. All right, and then we go again, as I mentioned, I guess if you look between the other one I called single board controller. Okay, so we had SBC, single board controller. Okay, and then here I'm calling it a single board computer. And the difference is the paradigm. So uh, I mean, you could still call Raspberry Pis or BeagleBones controllers if you want, but the difference is like a Raspberry Pi and BeagleBones, these actually use a general processor. Like it's an ARM processor, basically like the one in your cell phone, maybe not as powerful, but um, ARM processors or the Intel i7 processors or the AMD processors, those are what we call general purpose computers or processors. And what they do is you can just give them any kind of program and they can run it kind of thing. Once you get it into their dedicated machine language. But they're not like dedicated for one purpose. So if we go back and we think about the soundboards that we were looking at, where we had uh, the M32 or the Avantis soundboards that were processing, billions of bits of sound information and mixing them and sending them out somewhere else. Those things were dedicated. That's all they do, right? You can't surf the internet with those boards. They're dedicated for those specific tasks, but they do it so very well. Where a general processor like your Windows or Mac or even your cell phone or the Raspberry Pi or BeagleBone here, those have these general processors, and so and they're a lot more flexible. We can do a lot of different things with them because number one, they just have an operating system on there, and so we can use built-in tools to do network testing, or like I say, open up a web browser and search Google if you have a question that you need answered. Lots of different things like that. Okay, but these particular ones, the Raspberry Pi and the BeagleBone and others like this, like I say, they actually run an operating system. By default, it's typically Linux operating system. But then in that, you can program it using pretty much any programming language you want to choose, right? So we've been using Node-RED, where Node-RED is actually built on top of JavaScript, okay? But, if you're a Python programmer, then you can use that. If you're C++, you can use that. They even have shell scripting and something called Bone Script for the BeagleBone that is kind of cool. I believe the Bone Script is like Java or JavaScript also, but it's been a little while since I worked with it, but it's pretty cool. It had some cool features. All right, so here on the left we have a Raspberry Pi. This is a Raspberry Pi 4. That's a really cool device. It's got this one had built-in Wi-Fi. The Raspberry 3 didn't have built-in Wi-Fi. This also can support two HDMI, so you can run two TVs or monitors using HDMI connectors. These are many HDMI connectors on here. And then it has this one 40 pin these 40 pins over here. These are your I/O. And then on the right I have a BeagleBone Black. Okay, so this is similar to the one we use in the classroom. You notice this one is red. This one is actually certified for industrial use. And what that basically means is that the soldering and the wiring and stuff on it is basically a little bit higher quality, so that if you're using it in the industry, it's going to be subject to heat and dust and vibrations and other things. So it's just a little more rugged construction than the base one. So you can get the BeagleBone Black. The one we have in the classroom is just the standard one. It's on like a green board. And it's not the color that really matters, but like I say, how the soldering and some other aspects of it, that it's designed just a little more rugged in there. So they do have an industrial version of the BeagleBone. All right, so again, um, these provide a lot of I/O. I thought I had a pen I/O on that, but all right. So then we can just talk about the general purpose PC. So this could be a Windows PC, a Mac, or whatever, and these can be used to do control. Now, the default OS, like Windows and Linux and Mac OS, these are not designated real-time operating systems. Okay. However, there are real-time operating systems that you can download for a general PC. So you can have just an ordinary PC or laptop, and there are several different real-time operating systems that are out there. And again, the differences between the real-time or the general purpose GPOS is the fact that the real-time has some extra timing aspects to it, which you can use. So you can say, look, this task, again, if you think about the antifreeze coming out of the tank, you can dedicate and say, this particular task is very important. It needs to be done regularly, and I need to check the sensor and make sure that the sensor is telling me that the tank is not full, or when the sensor is full, I get that message within a few milliseconds, and then I get my message out to the pump and turn the pump off without any delays. All right, that's what we're talking about for real time. We get our information, we execute our program to decide what to do based on what the sensor inputs are telling us, and then act on that without any delays. And that's the huge difference between just a general Windows PC or when, like I say, it could be a Linux or Mac, it doesn't matter. None of those are true real time. But that doesn't mean that people don't use them for industrial applications, okay? Because, these PCs are running these great big 64-bit processors. They have tons of processing power, and they're really fast. And so even though they're not technically a guaranteed real-time operating system, if they're running like Windows, the fact that, you have so much processing power there that a lot of times we can actually use them and do control, and it'll work fine just because the thing's, has so much processing power. It's so fast that it gets done what we need it to do. Okay. And so you do see that, because the other advantage of this, especially if you're using a general operating system like Windows or whatever, is there's lots of programs out there that are available that can do some really cool stuff, especially now when we're looking at like AI technologies and stuff, or like image recognition tasks and things like that, that we can build upon very easy, so we don't have to reinvent the wheel kind of thing. Where if we were doing it like on a dedicated Arduino that I showed you earlier, it doesn't have the processing power, for one, to do too much graphics on it, and there may not be any tools out there to do it, so we would maybe have to develop those from scratch. Okay, so those are, so the advantage of using a general purpose PC with a general purpose OS is the fact that we can maybe incorporate lots of tools or applications that someone else did that are already available, and we have tons of processing power. And also tons of storage. So if we're collecting the data and storing it, then we can have a laptop or a PC with, terabytes of storage. All right. Then we have the industrial PLC. The industrial PLC is designed specifically for doing I/O in an industrial application. So this is basically a dedicated code paradigm where you create your program and you download it and it performs that program. So you can't like take a industrial PLC and open up the Firefox or Chrome web browser and do your homework in Brightspace. All right, it just you can't run um, a browser on it. It doesn't exist. Okay, so it has limited reflexibility, and they're often quite expensive too. Okay, but um, the thing is that they are designed for industrial applications. They are very solid. They are expandable with lots and lots of I/O, and they do their task very, very well. That last statement there, not designed for battery use. Not quite sure. That's to ignore that statement. I don't know. I can't remember what I was thinking when I was writing that, but it seems like auto check or something changed that word, and I can't remember what I was trying to say there. All right, and then we have hybrid devices and gateway devices. So like a gateway device, I talked a little bit about that before. A gateway device is a device, usually we use that as a term that's going to get us to the internet. So that basically it's usually like some sort of got some sort of built-in microchip and stuff. So when you talk about like switches, we talked a little bit about like switches and routers and things like that, right? Those are basically dedicated little computers that very, very simple in a way, but because their only job is to have those information packets come in and send them out a different way. And so those devices are very dedicated, um, very specific things. They can handle multitasking of lots of different incoming data very effectively. They can also at times, depending on their setup, they can do data collection or data analysis even, and storage. All right, and there's a lot of different companies like National Instruments and a bunch of other ones. I can't really think of some names at the moment, like Texas Instruments, and a lot of different designers and stuff have created different hybrid devices that can be used for controllers. Okay, so when we talk about manufacturing, right, or industrial controllers, the very first thing you got to think about is these things have to be reliable, right? They're in vibration and heat, lots of vibration and heat, so you need good soldering joints, good connections, so they don't vibrate loose. They got to run 24/7, 365 days a year. Right? You don't shut these down because Microsoft came out with a new update. Okay, I don't know if you've already had to do that with your computer this year, right? You come in, you turn the thing on, it boots up, and within 30 seconds of it booting up, it wants you to reboot so you can install an update. Right? That is just unacceptable for manufacturing. You can't just like, oh, let's go run this update. Okay, that's just mind-boggling to even contemplate something like that, right? You want this thing to be, you turn it on and it runs 24 hours a day, 7 days a week, every day of the year. You don't have to shut it down. Okay, And like I talked about those PLCs, right? They're quite expensive, but part of that is the fact that they are well supported. So if you have a problem, if one of your I/O cards go bad, you can call them up and get a replacement quickly. All right. So as far as hybrid devices, there's quite a few here. I have some links here. Like I say, this one here is called Compact RIO. This one's created by National Instruments. Okay. There's one called Siemens. There's the company Siemens, which does a lot of PLCs and stuff. They created this IoT series quite a few years ago now. Back in 2020, they came out with the IoT 2020, or maybe it was even before 2020, but they have an IoT 2020. So this is like it's a cross between like the BeagleBone and an Arduino. So it's kind of interesting. You have like a section of it that basically you can program using Arduino sort of code, and it has like I/O pins from that you can control real time, right? So that's the thing about like the Arduino that was running that dedicated program. That's basically a real time program, but then it also runs an ARM processor, kind of like the Raspberry Pi, that's running like a Linux operating system, or I think they also had another option, operating system for it, that may or not been a real-time operating system to do kind of the background stuff that doesn't have to be guaranteed real time. So, like I say, and then there's this one here, the USOM IQ, which was built on top of the BeagleBone. These are just three examples. There's way more in there, and I think in the notes section I probably have links to some other ones. All right, so that's it for this video.